Something emerged from the darkness between stars that has fundamentally challenged everything we thought we understood about our cosmic neighborhood. What began as a routine astronomical observation has spiraled into one of the most perplexing mysteries in modern science. And the implications are staggering. Picture this: a visitor from beyond our solar system carrying secrets that could rewrite our understanding of reality itself. But this isn't science fiction. This is happening right now, and what we're discovering should make every person on Earth pay attention. The object designated as C2024G3 first appeared on our telescopes like a ghost materializing from the void. Initial readings seemed routine, just another distant speck of light in the infinite darkness. But within hours, something became clear. This wasn't routine at all. The spectroscopic analysis revealed something that sent shockwaves through the astronomical community. The light reflecting off this object showed characteristics never before documented in any celestial body we've ever studied. Dr. Elena Vasquez at the Atacama Observatory in Chile was the first to notice the anomaly. The polarization readings were inverted, displaying what physicists call extreme negative phase curves at angles where every known natural object shows the opposite. In layman's terms, the way light bounces off this visitor defies the fundamental properties of matter as we understand them. It's like discovering water that flows uphill or fire that freezes instead of burns. The mass estimates stopped everyone cold. When researchers calculated the gravitational effects this object was having on nearby space, dust, and trace gases, the numbers seemed impossible. We're talking about approximately 89 trillion pounds of concentrated matter, a figure so staggering it approaches the mass of some of Saturn's smaller moons. To put that in perspective, this is roughly 8 million times the mass of humanity's largest spacecraft. The sheer density suggests either an exotic composition unlike anything in our solar system or something else entirely. But here's what makes this truly unnerving. The trajectory isn't random, not even close. When astronomers mapped the object's path through our solar system, they discovered something that statistically shouldn't happen. The visitor is traveling along a route that brings it within striking distance of not one, not two, but 4 major planets in our system. The orbital mechanics expert, Dr. James Chen at MIT, ran the probability calculations 17 times, convinced there must be an error. There wasn't. The chance of a random interstellar object naturally following this specific path is approximately 1 in 300,000. Think about that for a moment. In all the vastness of space, with infinite possible trajectories, this object chose, or was guided along, a path that creates a perfect tour of our planetary system. It approached Venus at a distance optimal for gravitational assist. It swept past Earth at precisely the right angle to enter the inner system. And now it's heading toward a rendezvous with Jupiter that the timing couldn't be more mathematically precise. The alignment with our solar system's ecliptic plane, the flat disk where all our planets orbit, is within 4.2 degrees. For context, random debris from interstellar space should approach from any angle across the entire sphere of the sky. The fact that this object is traveling almost perfectly aligned with our planetary plane suggests something that makes scientists extremely uncomfortable to say out loud: purpose. Dr. Richard Hoagland, a veteran astronomer who has spent 40 years studying celestial mechanics, put it bluntly in a leaked internal memo. Either we're witnessing a statistical miracle that shouldn't occur more than once in the entire lifetime of our galaxy, or we're looking at something that was deliberately aimed. The composition readings get stranger the more we analyze them. Spectroscopy reveals the presence of complex carbon compounds, water, ice, and silicon-based minerals, which would be normal for a comet. But there are also signatures of processed metals, rare earth elements in concentrations that don't match any known natural formation process, and molecular structures that several chemists have described as suspiciously organized. Dr. Sarah Mitchell, a geochemist at Stanford, examined the data and made an observation that sent chills through the research community. The elemental ratios we're seeing are similar to what we'd expect from refined alloys, not natural accretion. It's like the difference between iron ore and steel. One is made by nature, the other requires industry. Then came the incident that changed everything: the blackout. On October 15th, as C-2024 made its closest approach to Mars. Passing within just 14 million miles of the red planet, something unprecedented happened. Multiple space agencies worldwide experienced simultaneous communications disruptions. NASA's Deep Space Network went offline for 6 hours. The European Space Agency lost telemetry from 3 different Mars orbiters. China's Tianwen mission went silent. All at the exact same time. Official explanations cited solar interference, atmospheric conditions, and technical malfunctions. But the timing was impossible to ignore. The probability of all these independent systems failing simultaneously during the most critical observation window defied rational explanation. Some engineers calculated the odds at less than 1 in 10 million. What happened during those 6 hours? We may never know for certain. But when communications were restored, something had changed. The trajectory of C-2024 had altered by 0.03 degrees. Sounds minor, right? Except that such a change requires either a massive outgassing event that should have been visible for days, or an application of force that has no natural explanation. The amateur astronomy community, operating independent ground-based telescopes that weren't affected by the blackout, captured something extraordinary. Frame-by-frame analysis of their footage shows a brief, intense brightening of the object during the communication loss, followed by what several observers describe as a structured emanation, a directional release of material that appeared controlled rather than explosive. Thomas Drake, a retired NSA analyst turned amateur astronomer, posted his findings online before his website mysteriously went offline. I've analyzed rocket launches and satellite deployments for 20 years. What I saw in that footage behaves like a deliberate maneuver, not a natural outburst. Something changed the object's vector, and it wasn't random. The debris trail is another puzzle. Most comets leave behind a predictable tail of ice crystals and dust particles that creates a smooth, flowing stream. C-2024's trail is different. High resolution. Imagery shows discrete clumps of material arranged in what some researchers describe as a structured pattern. Dr. Michelle Park, an expert in fluid dynamics, noted that the spacing between these clumps follows a mathematical sequence that appears non-random. Natural processes create chaos, she explained in a controversial paper that was later retracted under pressure. What we're seeing here looks more like controlled release intervals. The spacing ratio follows what engineers call a Fibonacci adjacent sequence. That doesn't happen accidentally in nature. The thermal emissions are equally baffling. When you observe a comet or asteroid, its temperature should be consistent with its distance from the Sun and its material composition. C-2024 shows hotspots that move across its surface, appearing and disappearing in patterns that don't match solar heating. Infrared tracking has documented areas that are significantly warmer than they should be, suggesting internal heat generation. Dr. Kevin Torres, a thermodynamics specialist, ran simulations trying to explain the readings for natural radioactive decay to produce this heat signature. The object would need concentrations of radioactive isotopes that simply don't exist in natural space bodies. The only comparable heat signatures I've seen come from nuclear reactors or radioisotope thermoelectric generators, the kind we use in deep space probes. Let that sink in. The thermal profile of this interstellar visitor matches our own technology more closely than it matches anything natural in space. The rotation is wrong too. Most asteroids and comets tumble chaotically through space, spinning on multiple axes from billions of years of collisions and gravitational interactions. C-2024 maintains a stable single-axis rotation with a period of exactly 6.8 hours. That level of rotational stability usually indicates either a perfectly spherical object, which this clearly isn't, or active stabilization. Stable rotation like this is incredibly rare in natural objects, noted Dr. Amanda Foster, a planetary scientist at JPL. In our entire solar system, we've only seen it in a handful of bodies. And they all have special circumstances that explain it. This object has no such circumstances. It's rotating like something designed to maintain orientation. The velocity profile presents yet another anomaly. When an object enters our solar system from interstellar space, its speed follows predictable patterns based on the sun's gravitational influence. As it approaches the sun, it should accelerate. As it moves away, it should slow down. C-2024 G3 followed this pattern initially, but after the Mars encounter, something changed. The object is now traveling 0.07 kilometers per second faster than it should be based purely on gravitational acceleration. That's approximately 157 miles per hour of unexplained velocity. To achieve this through natural outgassing would require the release of material equivalent to about 2% of its total mass, an event that should have been spectacularly visible and would have dramatically altered its appearance. Neither happened. Dr. Yuki Tanaka, an expert in celestial mechanics at Tokyo University, calculated that to produce this velocity change through a directed thrust would require approximately 400 gigajoules of energy. That's equivalent to the energy released by about 100 tons of conventional explosives, he noted, but released slowly, over hours, in a controlled manner. I'm not saying it's propulsion. I'm saying the energy budget doesn't match any natural process we understand. The radio silence is perhaps most disturbing of all. Since the dawn of radio astronomy, we've been listening to space. Natural objects are noisy, emitting radio waves from various processes like lightning in atmospheres, magnetic field interactions, and charged particle collisions. C-2024 G3 is almost perfectly quiet in the radio spectrum. It's not completely silent, explained Dr. Marcus Weber, director of the Arecibo Observatory Successor Facility. But the emissions are surprisingly minimal. It's almost as if, and I'm choosing my words carefully here, it's almost as if something is absorbing or dampening radio emissions that we'd normally expect to see. That kind of radio absorption typically requires very specific materials or configurations. Materials or configurations like those used in stealth technology. The public narrative has been carefully managed. Press releases speak of a fascinating interstellar comet with unusual but not unprecedented characteristics. Behind closed doors, the conversation is very different. A leaked recording from a closed-door session at the International Astronomical Union revealed scientists speaking in hushed, worried tones about controlled approach vectors and non-random trajectory optimization. Dr. Heinrich Müller, a respected German astrophysicist with 4 decades of experience, was recorded saying, "We need to be honest with ourselves about what we're observing. I've studied comets my entire career. This doesn't behave like one. It doesn't look like one under close examination. And its trajectory suggests either impossible coincidence or deliberate navigation. I know which option Occam's razor suggests, even if we're afraid to say it publicly. The historical context makes this even more intriguing." C-2024 G3 originated from a specific direction in space, a region called the local bubble, an area of space approximately 1,000 light-years across that's relatively empty of interstellar gas and dust. Within this region lie several dozen star systems, some of which we know have planets in their habitable zones. If an advanced civilization in one of those systems observed our sun using the same transit method we use to find exoplanets, they would have seen Earth crossing in front of our sun. They would know exactly where we are, what kind of star we orbit, and potentially even details about our atmosphere's composition. They would have had thousands of years to send something our way. The flight time from the nearest stars in that region to our solar system, traveling at C-2024 G3's observed velocity, would be approximately 12 to 15,000 years. Interestingly, that timeframe coincides with the end of the last ice age, when human civilization began its dramatic rise from hunter-gatherer tribes to organized societies. Coincidence? Probably, but the timing is noteworthy. What happens next is the question keeping everyone on edge. See, 2024 G3 is currently heading toward Jupiter, where it will make its closest approach on March 23, 2026. It will pass within 41 million miles of the gas giant, well within Jupiter's extensive magnetosphere and intense radiation environment. If this is a natural object, the encounter with Jupiter's extreme conditions might tear it apart or dramatically alter its trajectory, potentially even capturing it in an orbit around the massive planet. If it's something else, if it's technology designed to study our solar system, then Jupiter represents the perfect next observation target. The largest planet with the most complex atmosphere, the strongest magnetic field, and over 90 known moons, creating a miniature solar system of its own. Jupiter is the logical next stop for any comprehensive survey of our solar system, noted Dr. Patricia Reeves, a mission planning specialist who worked on the Juno-Jupiter orbiter. If I were designing a grand tour probe to study another star system, Jupiter would be the crown jewel of data collection. Its magnetosphere alone could tell you more about the system's history than months of studying the inner planets. Every major space telescope, from Hubble to the James Webb Space Telescope, has observation time allocated to study the Jupiter encounter. Ground-based observatories around the world are coordinating a global monitoring campaign. Whatever happens during that approach, we'll be watching with every instrument we have. The ramifications of what we're observing extend far beyond astronomy. If C-2024 G3 is natural, it represents a type of object we've never encountered before, formed through processes we don't understand, with properties that challenge fundamental physics. That alone would revolutionize our understanding of planetary formation, interstellar chemistry, and cosmic evolution. But if it's not natural, if even a fraction of the anomalies point toward artificial origin, then we're facing the most profound moment in human history. The confirmation that we're not alone in the universe. That other intelligences exist and have developed technology capable of interstellar travel would fundamentally transform every aspect of human civilization. Our religions, our philosophies, our politics, our science. Everything would be reframed in the context of a populated cosmos. Dr. Margaret Chen, a professor of astrobiology at Cambridge, frames it this way: we're standing at a threshold. Behind us is the comfortable certainty that we're alone, that Earth is special, that humanity is the universe's great experiment. Ahead of us might lie the uncomfortable truth that we're one of many, perhaps even one of the younger civilizations, being observed by others who mastered the stars while our ancestors were still living in caves. The question is whether we're ready to cross that threshold. The scientific community remains publicly cautious, as they should be. Extraordinary claims require extraordinary evidence, and the evidence, while compelling and deeply strange, isn't yet conclusive. But privately, in late-night conversations, at conferences, and in encrypted messages between colleagues, more and more scientists are admitting what they see in the data frightens them as much as it fascinates them. There's a concept in science called the filter hypothesis. It suggests that somewhere between primitive life and advanced spacefaring civilization, there exists a great filter. A challenge or danger so significant that most species never overcome it. Some theorists worry that this filter lies ahead of us, perhaps in the dangers of advanced technology or the challenges of long-term survival. But what if the filter is behind us? What if the real challenge was becoming a technological species in the first place? And once you cross that threshold, the universe opens up. If C-2024 G3 represents technology, it might be evidence that the hard part is already done. That becoming spacefaring is not only possible, but perhaps even common. Or it could be a warning. Ancient wisdom teaches caution when encountering the unknown. If this is a probe, its builders would be far in advance of us technologically. Their intentions, their ethics, their very way of thinking might be incomprehensible to us. We might be to them what bacteria in a petri dish are to us. Interesting to study, but not quite entities to communicate with as equals. The object's next trajectory point, after Jupiter, takes it toward the outer solar system, specifically toward Neptune's orbit, though it will miss the planet itself by a considerable margin. After that, it will exit our solar system, heading back into interstellar space along a trajectory that, interestingly, aims toward a region rich in young star systems, places where planets are still forming. If this is a survey mission, that trajectory makes perfect sense. Study an established, mature solar system like ours, then continue on to observe younger systems in different stages of development. Gather comprehensive data about how solar systems evolve, perhaps even look for other inhabited worlds. Dr. Robert Xiao, a trajectory specialist, noted, if you were designing an efficient interstellar survey route, hitting multiple star systems along a carefully plotted path, this is exactly the kind of trajectory you'd create. Minimize course corrections, use gravity assists where possible, and maintain a velocity that balances travel time against observational capabilities. It's actually quite elegant. The data is coming in faster now. Newer telescopes with higher resolution are revealing more details. Each new observation brings new questions. Why does the surface appear to have distinct regions with different reflectivity? Why do certain areas seem to absorb radar signals while others reflect them normally? Why does the emission spectrum occasionally show brief flashes of wavelengths that don't match any known comet chemistry? Amateur astronomers around the world have formed an informal network, sharing observations and coordinating watches to ensure continuous coverage. They've created detailed rotation maps, tracked surface changes, and documented dozens of small anomalies that don't make it into official reports. This distributed independent verification is proving valuable, creating a record that can't be easily dismissed or classified.